Hi class, we are going to talk about bubble sort algorithm. So we are going to assume the same thing like in the selection algorithm, selection sort. We are going to sort from smallest to the biggest number. So what we are going to do is we will start with the beginning of the array. We will compare 0 and num0 and num1. If they are in the wrong order, then we switch them so that it's in the right order. And then we will do from num1 to num2. And so at the end, what happened is the biggest number will end up in the last number, because by this comparison, the that's why it's called bubble sort. It bubble up to the end, to the last array element, and then we repeat this basically and do it again from the beginning and then switch. But we know that the last one's already in place, so we don't have to do anything. And so we repeat until the swapping is only in the beginning, and once the 0 and 1 is in place, then you're done. So the other observation is kind of the same. So we are building, however, though, from is like the largest number at a time. So in the selection sort, we have the smallest number in place first. In bubble sort, we have the largest number in place first. In a way, just because how we decided to it, we can do it the other way as well. So but the difference is, in the swapping, in the selection sort, we actually find out the smallest number in the whole array first and then swap once. But in bubble sort, we keep swapping and swapping and swapping the adjacent elements. So in this particular way that we are going to implement, the right side of the array is actually sorted already, which means the place where there's the bigger numbers. And then in the left side is so the smallest indexes are unsorted and shrinking. The mechanism, like I shared before, I always think about how it will work in terms of in the machine language, right? Or the machine the programming way, right? So now we will start the partition index not equal to 0 but equal to the last index. We will compare num1 to num0 and num1 and swap if needed, num1 and num2 swap if needed, num2 and num3, and so on. And then once we went through the loop, then the partition index will be decrement by 1. And we do it again until where the partition is. So let's look at the code. So the same, I put all the comments and my thoughts in there, the mechanism, so that I keep track of what my thought process. And then I decided to do a compare and swap function, basically to do the mechanism step number 2. Let me see if I do number 3 also. I actually don't think so. So I would just compare the adjacent numbers and start from num0 and swap if they are not in order. So that's for mechanism number 2. So let's first of all write this function out. This is my how I designed the function. So I will compare adjacent numbers, swap if they are not in order, start from a start index and a start index plus start index plus 1, and then the next pair actually. And then basically repeat this process until the end. And then the assumption is that the last index is larger than or equal to the start index, just like in the selection sort function that we used. Parameters, we have the but this time we have to pass the array in as by reference, because here we are going to swap the elements in this function. We have the start index, we have the last index as parameters also, and inside we are going to use the swap function. Swap function is like the last one, so we are not going to talk about it. So let's implement this function first. So basically what we are going to do is, starting from the start index, we will stop when is equals to the last index, and then is I plus plus. This is actually from the beginning to end. So what we are going to do is, if the we will compare the I and the I plus 1, AI and AI plus 1. If they are not in order, meaning that the smallest one is not in the beginning, basically. So then we will swap them. And if actually they are in the right order, which means that AI is smaller than AI plus 1, then I will leave it alone. And then I think I will just do an assert like before. I will check to make sure that the start index is always smaller than or equal to the last index. And then nothing to return. And we will just continue until the end. One thing to make sure though actually is that we want to not go past the index. So we actually have to use I smaller than last index, because we have to take care of the case, we actually will add 1 to the last index, or we'll add 1 to I. And so I plus 1 will pass the last index if we don't fix the basically exit condition. So let's test the function though. So let's see if it acts as we expect. So let's do a compare and swap, pass in the array. The start index is 0, the last index is this, and then we'll print out. So basically we compiled it, so let's run it. And so let's see, so supposedly the biggest number will bubble up to the last index. It looks like it did. So let's do another test to see if it works. We have to compile it, and then so 16, it seemed like no matter what, 16 always float to the right hand side, which is what we wanted. We would test again to just make sure it works. Yep, so 42 floated to the top also. So it looks like this function is working. So now let's comment it out and see. So if we want to implement the whole mechanism, right? So the first we are starting with partition index equals to the last index, which is array size minus 1, and then we will compare the adjacent numbers, but we have to do a loop from beginning to end. So let me see. Actually, compare adjacent starting from a swap if not in order. So we would do this until the end of the array. We would do I plus plus, and then what we are going to do is basically just do this swap and compare. However, the starting point actually is always is it always I? So no, it's actually always 0, and what end up changing is the partition index. We have the same basically thing going on. So it's the partition index. Yes, I think this makes it easier to read the code. And so what we do is we just compare, and then we update the partition index, which is built in. Basically, the step number 3 is done here as well. And we repeat until partition index is equals to 0. And so actually what needs to be done is this need to start here, and then yes. So you see why it's nice to write down the mechanism, because I can check. That's what I realized. The partition index actually starts from the end, right? And so we actually don't even need this line now. So partition index start from the last index, and then it will when it's larger than or equals to 0, then it will decrement by 1, and in each step we compare and swap in the unsorted portion of the array. So let's compile and run it. So 6 numbers are all there. -4, 3, 10, 16, 41, 42. So it seems like it's sorting correctly. Compile it, run it, -404. So it looks like and that's how we test our function, right? So of course I will test it, but also at the same time I will really try to understand each line of code if I've missed something, and then would I be able to optimize it, for example. So I'm showing you part way of what I would do. So I hope this is helpful for your assignments or your further programming endeavor. So we are just going to talk about multi-dimensional array in the next video. See you soon.